Alrighty, hey AP Pre-Calc, this is going to be our exponential functions, context, and data modeling. So let's run through this pretty quick. The function f is decreasing. The table below gives values of the function for the selected values of x. While using the calculator, write the exponential function to model the data. Alright, so let's see what we know. Recall that an exponential function is in this form. F of x is equals to a times b to the power of x, where a is our initial value, or perhaps our pivot point, and then b is our our growth or decay factor. So knowing that, I think based on the table here, this will tell me my pivot point or my initial value. So I know that a is equals to 25. Then as far as finding b, recall that geometric series are pretty much in the same format as a given exponential function. And so if I take one value and divide by the previous one, in most cases, this should give me the growth or decay factor. So if I take 15 divided by 25, I get, what is that reducing by 5? I get 3 over 5. And so b is equals to 3 over 5. Now that I know that, I can just combine everything that I know and put it into one equation. So I'll say that the function for this table is described as f of x is equals to 25 times 3 over 5 to the power of x. Awesome. Now let's move on to the second problem. So it says here, sometimes data from an exponential function does not display a proportional growth pattern. This is due to vertical translations of the function. However, if we can add or subtract a constant amount from the output values to reveal a proportional growth pattern, then the initial function is also exponential. So that's going to be the key thing that kind of helps us with these problems here. So let's go and try and figure these out. So let's see. Let's see if we can figure out what we need to add or subtract by to reveal something that is perfectly proportional, and then use that to write the equation that models this original function. Let's take a look. It's just there's really no clear-cut method to this as far as doing it this way. So as far as trying to figure out what we should add or subtract by, I don't know. It's all about testing a few numbers until it works out. So, for example, I might just add 1 to all the current output values and see what my new output values will be. And fingers crossed, it becomes something that's equally proportional from one number to the next. So let's observe. It'll be 8, 14, 26, 50, 98. It's not necessarily working out. And if I try to add 1 again, I get 9, 15, 27, 51, 99. A lot of these are divisible by 3. I perhaps can come up with a specific factor that multiplies to give me the next number. However, it doesn't seem exactly the easiest thing to be proportional. So instead of adding here, maybe subtract and go the other way. So let's go and subtract. Here, I got a cough. Oops, sorry. All right, let's say we subtract by 1. Notice when we do this that we get 6, 12, 24, 48, and 98. And if you compare the new output values, for sure, from one number to the next, it is perfectly multiplying by a whole number, right? In this case, multiplying by 2 each time. And so with that work, we can know two things. One thing is the base, right? The ratio in which I am going to be multiplying by each time. So I know this would be at least saying 2 to the power of x. And as far as the a value goes of this given quote-unquote exponential function, right, what goes in this spot right here, um, it will be based on the initial value that we see for the current new output value. So it would be 6 because that's associated with this x value of 0. So I'll say 6 times 2 to the power of x. So currently right now, this formula that we derived using the previous rules like in this one only models the new output values. So right now we're not quite done with the problem. We want to write a function that models the previous, right? The actual function that we should be. And so to make sure that we get back to our original function, we need to undo one simple step. We just need to make sure to re-add the 1 that we subtracted by originally. So if this equation models this, as long as I add by 1 to the whole model, it should result back into our original function. And we can see that this works out if we put this into our calculator. And so let's see if this table of numbers is reproduced if I put it into my table in my calculator. So you see here, I'm going to go in the table here. And I might have some stuff already in here. Let's just go ahead and delete it and put in the new supposed function and see if it holds true. 6 times 2 to the power of x all plus 1. And then we'll press enter to submit it. Let's look at the way the table is being set. 1 to 20 seems like too much. Maybe from starting from 0 to 4 is better since that's the actual given points that we have here. So let's take a look. Let's go ahead and press execute. Let's go and find the table now. And we see the set of output values match the current function that's being described to us. So this is perfect. The equation we make is exactly what we want. So this general idea might be kind of hard to kind of have clicks since it's kind of just like, I don't know, testing a few numbers till it works so you see a pattern. If you don't like this method, I'll show you another one at this third example. All right, here's number 2, or sorry, part B. So again, I'm looking just to add or subtract by a few numbers here by a constant to see if I can find a pattern relatively quickly. And so again, you might subtract by 1, subtract by 2, maybe you'll find something. But here, I'll let you know if you add by 2 right off the rip, you'll get 4, 12, 36, 108, and 324. And so eventually you'll start like, messing around the numbers, adding by certain numbers until you kind of feel like you get a certain pattern of numbers, right? I call it the math tingle, right? Kind of like Spider-Man. He's like a tingle when, he senses something insane or something's about to happen. Like you can kind of anticipate it. And here I can anticipate that from one number to the next, I'm just multiplying by a ratio of 3, right? I'm multiplying by 3 each time to get from one value to the next. And so that's exactly what I'm looking for, right? So this is really ideal. So now that I know that, I know for a fact that my base should be 3 all to the power of x. My a value is again the current initial value or pivot point of my new output value. So I'm going to use this 4 here. So I'll say 4 times 3 to the power of x. And then I want to undo what I added by so into this equation so I can go back to the original function. So I'll say minus 2 all equals to f of x. Boom, done. Right? Some problems are not as easy as these, where you might just add by 1 or 2, or subtract by 1 or 2. Sometimes you want to add a few more than that, or so it all really depends on the problem. It's not as obvious as you think, and it's really not obvious at all. Maybe you'll like this second method I'm about to show you. Okay. Sorry if I'm coughing a lot. I'm still recovering from a sickness. All right. So let me show you the second method. Right. Overall, for this style of problem especially, if we know for a fact that there is some vertical translation involved, then there's an assumption that can be made about the general equation. It won't look the same as this. It'll look mostly the same, but there's a few more components that we would have to add on that we don't know. Okay, it's gonna be the same kind of format that these have been so far. So let me write them down. Let me write this down for you. So it should be in the form of y is equals to um, a times r to the power of x plus b. So I'm kind of redefining my variables a little bit. So I don't use b as my base anymore. Let's just use r as the ratio for my base, and we'll use a and b separately. So now I'm trying to figure out what the a is still very much the pivot point, the initial value, but now b is dictating how much my vertical translation is. So we're going to be able to solve for all these components just by using the information that's provided to us. So no adding or subtracting here. There's no need to guess and check type vibe. There's only one thing I do need to find, and that's my ratio for sure. So the one way that we found our ratio prior was that we would try to do the first difference here. So as I try to find the first difference, what is that? 63 to 31, I'll subtract 32. From 31 to 15, that's subtracting 16. From 15 to 7, that's subtracting 8. And then that's subtracting 4. And so based on my first difference, I can notice that I'm multiplying by 1/2 each time. And so at least doing that, this can give us our ratio. So I know what goes in for my base here. So this is the information I have so far. Let's not say y. I kind of prefer f of x. Let's say f of x is equals to a times 1/2 to the power of x plus b, right? We at least need this to be set up at least to be successful for the rest of this method. So now that we've done this work, we can now move on by setting up a system. So as long as you agree with my math statements here, this should work out. So let's plug in 0 into the function. Let's say f of 0 is equals to a times 1/2 to the power of 0 plus b. We know for a fact that if we plug in 0 into this function, that I should get 63 back. So technically this is all equals to 63, which is great. And so if I were to simplify just a little bit further, I would say let's imply that this is all equals to a plus b is equals to 63, right? Recall that 1/2 to the power of 0 is simply just 1. 1 times a is just a. And then we want to write another equation if we want to solve a system. So let's actually make a system first by plugging in another number. So I might say f of 1. Let's do the next number. Why not? F of 1 is equals to a times 1/2 to the power of 1 plus b. And I know for a fact if I plug in 1 for my x function, I should get 31 back. So let's take a look. 31. And so if I simplify that just a little bit further, I get 1/2 a plus b is equals to 31. And now with these two equations here, I could design a system. Let's go ahead and bring that over to the right hand side just a little bit so I can work with them a little bit further. And so now this is looking at it as a system. I can solve this system doing whatever method I like, either elimination or substitution, but I think elimination is the quickest as long as I take the bottom one and subtract by it right now. So I can cancel out b and solve for a. And it seems like I get negative 1/2 a. Let me write this in black actually. So negative 1/2 a, or sorry, not negative 1/2 a, I apologize. Just 1/2 a, right? A whole a minus half of a, I still have half of a left. And then my b's should cancel, so I have no more b's. All equals to, what's 63 minus 31? What is that, 32? 32? And then if I solve for a, multiply by 2 to both sides, I get a is equals to 64. Now that I know what a is, I'll just take this and re-plug back into one of the equations I derived, and we should be able to solve for b. I'll pick the first one here. So I'll say 64. Let me do a different color to know that I'm plugging stuff in. 64 plus b is equals to 63, right? Right now I'm just plugging into this equation here. And solving for b, I get b is equals to, what was that, negative 1? Really? Okay. Not so bad. I think that kind of makes sense. Yeah, it should be negative 1. All right, and then now that I have every component, I'll just plug this back into my equation. So I have f of x is equals to 64 times 1/2 the original ratio to the power of x minus 1. Boom, done. All right, so whatever method you like, this is a lot more direct for sure, but I think it's a lot more steps. Right, this method is a lot more, I guess, hand wavy, and then you kind of just have to think just a little bit, but it's definitely a lot faster if you can see it this way. Like for example, I could have gotten all these numbers a whole lot faster if I had just seen this grouping of numbers and said add 1 to it. All right, that's 64, 32, 16, 8, and then 4. See that I'm multiplying 1/2 each time, and I pretty much have every single component I need to write the same formula, right? That 1/2 that I found is going to be my ratio. I know my initial value should be the initial value of the new grouping for my output value, so I'll say 64. And then the number that I added by, I simply just need to subtract now to get back to the original values, and so subtract by 1. And you notice that's the exact same equation that we derived here. So whatever method you prefer, you like a more direct way, do the direct way. You like the whole hand wavy stuff because you can see it, more props to you. Okay, I would say let's lean towards this because that means you can finish problems a lot faster on your AP tests as well as my test. Okay, let's move on to number 3. All right, let's go through it relatively quickly. Take a second to read it. So I don't have to read it on the video. So pause now and read it and then continue on a count of 3. 1, 2, 3. Okay, hopefully you read the problem. And then now let's go ahead and define the information that they gave us, right? So I'm not going to start off with working on A. Let's just define for a fact that I know that at f of 2, right, after 2 minutes, I know there's going to be 47 people. So if I plug the 2 into the function, I should get a result of 47 total fans in the stadium. If I plug in f of 20, I get 2602. Right? And so that's just information that was given to us, and now we're going to use this information to write and derive more facts from this to write the answers for part A, right? Writing two equations that help us find A and B. So hopefully you agree with the statement that f of 2 is equals to 47 is implying that the function, by the way, this original function here, this implies that uh, A times b to the power of 2, right? I'm plugging in 2 into this function, right? Supposedly. If I did that, if I plugged into this function, I should get a result of 47, right? They're already claiming that this right here is our function. We just don't know what a and b are. And figuratively, if I plug in 2 into it, I should get 47. I don't know what a and b is yet, but this is a good start. If I do the same thing for my second equation here, right? If I plug in 20, it should be AB to the power of 20 is equals to 2602. And so technically, I've kind of created a system here in which I'm not going to solve it the same way as elimination and substitution, but I might use substitution here. But it's the same type of vibe for sure, right? Now that I've created a system, I can try to do substitution here and be creative to make this AB square appear inside this particular expression, or in this particular term. Because technically I can make that happen. If you recall our product rule, I can split this up technically, right? Let's take a moment and split up this second equation here. I can, instead of saying AB to the power of 20, I can say AB squared times B to the power of 18, all equal to 2602. Because if I do that, I've been able to make AB squared pop up mathematically, and I know what AB squared is. We said that was 47. So I was going to plug that in for our spots of AB squared. So now I'm going to say 47 times b to the power of 18 all equals to 2602, right? This implies that. And at this point, it's just about algebraically solving for b. So I'll divide by 47 to both sides. I get b to the power of 18 is equals to 2602 all divided by 47. I didn't bother putting this in the calculator, but I'll do it now just to show you that if I did, I'm not really going to get a nice number back. So if I did 2602 divided by 47, see, it still kind of tries to stay as a fraction because if I press the fraction, or sorry, decimal button, it does give me a decimal number, but I'm pretty sure it's irrational, or it goes on for quite a bit, and I don't want to estimate it quite yet as I work through the problem. So I'm going to keep it as a fraction so I have all the numbers here, so I don't really lose any significant figures. So now at this point, I just want to take the, what is it, the 18th root of both sides, and I should get the 18th root of 2602 all over 47. Now that I have like a concise final answer step, right? B is equal to something. Maybe perhaps I'll put that to the calculator and estimate what that is. I think that's kind of fine now. So now, since I already have this stored as my previous answer, I'll just say what is the cube or 18th root of my previous answer, and it should have every single number possible in my decimal here. And so uh, that doesn't feel right. Let me try it again. I recall that number being differently. I could be totally wrong. Let me just double check that that's right. So I'll do shift 18th root of 2602 divided by 47. I get the same number. It's fine. All right, it's probably fine. So we'll estimate to about the 4th digit here, just to be as accurate as much as I can, at least, since I know it kind of goes on for a while. Let's try to get some decent accuracy here. All right, we'll go up to the 10,000th digits. Now that I know what B is, though, it's all about solving for A, and I can definitely solve for it algebraically. And I kind of like went ahead and started working on B almost immediately. Just FYI, this part right here answered part A, and now the rest of the work that I'm doing is helping me solve part B. So sorry if I didn't specify that. All right, regardless, now let's go and solve for A. So I'll simply just plug back in what I know for B back into one of my original equations above, right, one of these guys, and then I should be able to solve for A. Let's just pick the first one. So I'll say A times the 18th root of 2602 over 47 squared all equals to 47. And so you might be wondering, well, why don't you just put your estimated number inside for this? Well, I kind of don't want to use my estimated number yet. If I have my exact number still in my calculator here, I can still kind of work with it until I find the exact number for A, right? Since I'm using my calculator for some of this work. Okay, so I'm kind of just one step away now from solving for A, by the way. If you can't see, just divide by this whole chunk here, put to the other side. And so I get A is equals to 47, all divided by the 18th root 2602 over 47, all to the power of 2. All right, and this is really, really ugly, but that is algebraically exactly what the answer is. And so it's just a matter of plugging it into the calculator to figure out what it is. But there is an off chance that this is on the calculator section, or sorry, on the non-calculator section, and I would ask you to solve it algebraically. And this is how you would solve this A and B value algebraically. But if I want to, it's not the calculator, of course, plug it into the calculator and let me know what number this is. So let's take a moment and do that. I should say 47 all over the 8. Oops, whoa, didn't mean to do that. Sorry. Sorry about that. Let's delete the cosine. We'll say the shift caret 18th root of, what is that, 2602 divided by 47. Oh, I lost my parentheses that I had out here. Let's go and put those back. Put a parentheses there. And put a parentheses here. And then we want to square it, right? This is disgusting. However, we should get a nice number here. Nice-ish number. It's maybe around 30, I believe. If not, we did something wrong. All right, perfect. It is all good to go. So A is about 30.0890. Perfect. All right, so we estimate what A and B are, and those would be the answers for part B there. And if you really want to double check if this is good, we could quickly graph these points into our statistics tab and say, what is it, at 2 minutes and 20 minutes, the associated values or associated fans at those times were 47 as well as 2,602. If I put this into my statistics and then calculate a regression, an exponential one, we should get the same numbers here as far as A and B go. So inherently what I'm saying is our function f, we actually know exactly what it should be now. F of t is equals to, what is it, 30.0, whoops, 30.0890 times 1.2498 all to the power of x, right? That's what we're claiming here. And so if I do my exponential regression, we should see that we do get the exact same A and B values. So life is good. Life is really good. So our answer is looking pretty right. All right, let's quickly do number 4 now. All right, let's see about number 4. So number 4, it says the number of bacteria B in a particular culture can be modeled by the exponential function B of t is equal to 17 times e to the 0.31 t, where t is measured in hours. Recall that Euler, this is Euler's number, E, right? I'll write it out for you. Euler, not Euler, okay, not Euler, Euler. Is about this number here. It's definitely irrational though, it does go on forever, but this is how much we'll estimate in terms of that. All right, so let's take a look at what's being asked here. It says let A of t be equals to A times B to the power of t, be an equivalent expression for B of t. So all they're saying here is if you compare the function here and then compare it to this one, we can write an equivalent expression in this formatting. I'll be honest with you, this function is kind of for the most part already in this formatting. Because they're just trying to find the value of A, which is the number in front of your base. In this case, it's quite obvious to see that the number in front of the base, right, the base being E, is just 17. right? A is equals to 17, the number directly in front, right? I'm not sure why they're asking for A, but I guess it's good to know that our pivot point is 17. But I know this is not being asked, but I think a better question that people get confused about is, what is B actually? What is my base here? So if you want to make a guess, make a guess. What is your base? And if you said E, you are technically slightly wrong. It's not just E, right? I can totally understand why you think it is just E, right? It looks like it's the only base here raised to this exponent. However, if you look at this equivalent expression that we should be in, the only thing in the exponent is T. If you notice in the previous, or not previous, but the actual function that we have, there's something more else. There's something else that's there, right? It's not just t, there's also another digit, right? There's 0.31. And so I should rewrite this. All right, be 17e to the 0.31 all to the power of t. I just applied my power rule. And so now if I look at this equation, this definitely looks a lot better because I can clearly define what b is, and now that t is the only thing in the exponent, this is a valid equivalent expression. So b is really e to the 0.21, or sorry, not 21, 31. I think it's a better question that's being asked here. So be mindful of that. Don't be too, what is it, bothered if you couldn't tell, but now you know. All right, then let's find the average rate of change of b of t over the intervals of t equals 1 and t equals 7. So this is just some recall on what the average rate of change formula is, in case you forgot. So again, average rate of change, the formula for this, let's say AROC is f of x2, sorry, f of x2 minus f of x1, all divided by x2 minus x1, right? Change in y over change in x, essentially, if you remembered it that way. And I believe I am given my x2 and x1, right, based on these values here, right? This is my x1, there's my x2, and we just need to plug it back into the function that was provided and figure out what this is, right? So I set up the formula for you. It's about just plugging and chugging at this point. So in essence, I have 17e, so 0.31 times 7, all minus 17e to 0.31 times 1, all divided by 7 minus 1. So at this point, I couldn't do much more by hand besides simplifying that 7 minus 1. So let's go ahead and just plug this into the calculator and see what we get. So I'll press menu, let's press 1. Let's see, let's plug this in. Let's do the fraction button. 17e to the power of 0.31 times 7. The cursor is still in the exponent, so let's scroll a little bit over. Minus 17e, where's my e button? There it is. 0.31 times 1. So my numerator looks exactly how my numerator should look based on my work. Let's now go to my denominator and say 7 minus 1. And I'll just make sure to double check that everything looks good. And it definitely looks good, so let's press execute and see what number we get. So my average rate of change is 20.9521. The context of the problem is about bacteria culture, so not like the culture of bacteria, but you know what I mean. Bacteria per hour, right? So this is how much I'm increasing by. So that's the average rate of change, right? That's how much change is occurring. It's increasing by this amount every hour, right? At least from t equals 1 to 7. Of course, it's exponential, but as far as the rate of change from 1 to 7, this is what we say. It'll probably get larger as the hours go on. All right, let's do some more calculator work, right? So the part C here is a mix of both calculator and non-calculator. It says find the values of T when the number of bacteria in the particular culture is 1,000. So what they're saying is, at least by hand, if you were to set this up, you'll say 1,000 is all equals to your equation. And you're wondering what time would it take for this equation to give me that output of 1,000 bacteria. And so you can either set it that way and solve by hand. I'm going to first do it in the calculator so you can see what the answer should be, and we can move on from there. So let's take a look at the calculator. How would I do this? So I'm just going to plug in the right-hand side, really just the equation into my graph. So let's take a look. Let's press menu. Let's go down to graph. let's delete what we currently have and change it to the correct formula. Let's delete that and say 17e to the power of 0.31 times t, but then there's no t button, and definitely don't use that t right there. Just do x in place of a variable. Let's press execute to submit this in, and I know it's submitted because the equal sign is highlighted there. And then I'll press draw, and I don't quite see a whole lot of it. And I don't know if doing gsolve right now would work. I think sometimes you gotta zoom out just a little bit to see a little bit more, but we'll give it a shot anyways. And since I'm given the y value here, and I'm trying to figure out what x value will make this statement true, I'm gonna do xcal because that's what I want to figure out. We want to calculate for x, and plug in 1,000 for my y. Will it do it? See, it says not found, so that just means you didn't do anything wrong. You just kind of have to scroll up a little bit, zoom out to see more of your graph until you have like enough info. And I think for sure that this looks pretty good. I see quite a bit here. And so now I'll do it again. Let's see. Let's press gsolve, shift gsolve, xcal, plug in 1,000, and yeah, now it pops up. Perfect. So now I say the x value associated should be x is equals to, what does that say? 13.1437. And so when we solve this by hand, hopefully we get the same number. So here's how you would do it by hand. There's some pretext to this, which I might say over here. Recall that a natural log, right? Natural log of x, the same thing as saying log base e of x. All right, so we'll bring in logs a little bit because we will see that in the future. And then another good property to recall that log base x of x to the power of b, right? We're saying x to the power of b is the input of this log. If for some reason the base of your log and the base of your input are the same, the resulting simplification is simply your exponent. So we're going to recall to these facts once we kind of go through this problem. So let's take a look how we do this by hand. Naturally for us, we want to divide by 17 on both sides. 1,000 over 17 does not simplify any further unless I want a decimal number, which I don't, so we'll leave it alone. All equals to e to 0.31t. At this point, if I want to cancel out e, I would take the natural log of both sides. So I'll say, let's do this part in red technically. Let's say the natural log of blah blah is equal to the natural log of blah blah. And we'll throw in the current blah blahs into the inputs of our natural logs. Right? We're taking the natural log of both sides. This is what I mean by that. Left hand side, not much really happens. On the right hand side though, the base of natural log is base e. The input's base is also e. So right now this property is being applied. So that means that the resulting thing of this right hand side is simply the exponent. So let's rewrite it. Let's go up here. I'll now say that the natural log of 1,000 over 17 is all equals to just 0.31 times t. And now I'm just one step away from solving for t, right? Just divide both sides by 0.31 and then you're pretty much done algebraically, right? So we solved this thing by hand. Now, it's not really useful, to be honest, because I really don't know what number this is quite yet. You'd still have to put this into the calculator, perhaps. But if I didn't have this on the calculator section, this is an acceptable algebraic answer. Okay, I'll look for this. But let's just check if we did this correctly by hand. So let's take a moment and plug this into the calculator. Let's press menu, 1. Let's say natural log. Let's do the fraction button first, actually. Natural log, parentheses, 1,000 over 17. Oops. Let's move out and then do parentheses. All divided by 0.31. Is that the same? I thought it wasn't for a second, but yeah, it's actually exactly the same, right? But I rounded at this digit here, which would match the number that's provided when we did it by the calculator. So life is good. Life is good. All right, one last problem to finish it up. We're already 34 minutes deep. Sorry, dude, I'm a talker. I thought I could finish this way faster, but whatever. All right, the function f is increasing. The table below gives values for a function has selected values of x. And an exponential regression y equals ab to the power of x is used to model the data. Find the exponential regression model. So at this point, we just need to plug in this table of values into our calculator and do a regression. So this one should feel pretty familiar. So let's plug these numbers in. I'll say -1. Oops. -1. Let's not do that negative. Let's do this one. -1. 0, 1, 2, 3. And this is 1, 2, 9, 51, 247. Let's press calculate. Regression. Let's scroll over for exponential. And then pick the one without Wheelers because they're not asking for that one in this problem, right? They're asking for just regular one. So we'll do F2. Oops, F2. And then we have our values. And so this where I'll just round up to the fourth digits. So that 10,000th place. So I'll say f of x here is equals to 2.8308, right? That's the a value. Times b, which should be 4.1. Oh, so this is where I would say, notice that we're rounding at the fourth digit, and we'll use the next number to really figure out what number that would be. So it seems like it's this 5 here, we'll round this up to 10, which technically also rounds up this number. And so I'll end up saying 4.4.161, but I'm also going to add the extra 0 here. And so you might wonder, well, why are you doing that? Why are you rounding up to the 100,000th digit, right? You said the fourth number, Mr. Bowie, and yet you're rounding it with this extra 0 here, and that doesn't make any sense. I don't even need those zeros. In chemistry class, we don't even need those or whatever. To be honest with you, I agree with you. You probably don't need those. I'm just being a little bit nitpicky here, and I'll explain why. Okay, you can skip this whole part right now, and it's just fine when I start talking about B. I'm about to yap so much about part A. Okay, I apologize. But the reason why I round like this, and again, this is probably so insignificant. Honestly, I bet I don't know how important this is, but I think it's important. Okay, so the reason why I rounded it that way is because and include all the zeros because I want to know when I start to round. So for example, if I erase all the zeros contextually for you as a reader who is interpreting these numbers, if I left it like this, it feels as if you rounded on the fourth digit. And that is not what happened, right? And so if I was like trying to guess what number this is, right, the number that's currently in this spot right here, it can be a multitude of things. It can either be a 1, a 2, a 3, or 4, because I'm assuming that I'm rounding from that spot, which rounds down, which will give me this 1 that's here. And that's kind of inaccurate. I didn't round at that spot. In reality, the number that was currently there was 9, and you can see that's true based on my calculator right here. Like that fourth digit was actually 9, and before that was actually 5. And so it's basically you want to include all these zeros to give context to some reader. Sorry, I'm missing a 1. To give context to some reader who looks at your math to know like, oh, how did they get this number? When did they start to round? Oh, that means they started to round right at the fourth digit. However, it was the fifth place that helped you round this digit to 0, which coincided to give you the 1 following up, right? So it gives more context as to how you rounded. And so the margin of error, if someone was to try to derive what possible estimate this number could be, is a whole lot less if they know exactly where you start to round, right? In the grand scheme of things, it's probably not all that important because this number is a whole lot bigger than the fourth digit. However, I think it's still good practice to do, right? I think what I said in class was like, imagine an alien, they come back and they were trying to like interpret the data in our iPads or whatever, probably not our iPads, some more, important things. And, they saw some rounding and they just didn't know where you started to round, right? And so the possible difference in what you round to can be a whole different position in space than they're looking for, And so you want to give people the right directions. And so I'm not sure, again, this is probably nonsense what I'm saying, but there has to be some practical use in some real world setting in terms of like, astrophysicists or in terms of like, shooting a rocket in a specific location, right? The rounding matters, okay? Rounding matters is all I gotta say. All right, yapping over. All right, sorry, I don't know how long that yap session was, but Let's get the part B, which is a lot faster. Okay, it says find the expected value of x equals 4. And if I was using the equation that I estimated from, of course I could just plug an x into this right here, or plug in 4 into that x and figure out what that is. But since I'm using the calculator, I might as well just use this equation that's already given to me right here and plug in 4 into that, right? It has all these extra digits, which is very nice. I want to know exactly what digit I'm getting to without too many rounding. So I'll press copy here. And it doesn't say the equation yet, but if you press enter, it should take the previous equation we just had and input it into the first line for our graphing. So notice if I press execute, it goes back to the screen, but if we press menu and go to graph, the new equation should be in there. And right now it's not inputted quite yet. So maybe I'll scroll a little bit to like unhighlight it and then press execute to now submit this equation in there. And then I'll press draw and then I'll press shift G solve. And now that I know what x value I have, we actually want to calculate for the y value. So I'll press y cal and input the x value that I was given, which was 4. And so at 4, I get this somewhat large number. I get 848.5709. Alrighty. That is it. I hope you have a wonderful day. Like the video, subscribe. I'm trying to pump this number up so I can start to get some pennies on my YouTube channel. Okay. So appreciate you watching to the end. I hope you have a wonderful day. And yeah, that's it. Bye.